Dear students, so in the last 3 previous videos we have been dealing with the strain energy method, that is the theorem of least work, to analyze indeterminate beam. So this is another problem. The difference in this problem is that earlier we were dealing with the problems which involved the ds value as 1, which means we were having just one redundant for the calculation. But what if the structure is having ds value, that is degree of static indeterminacy, greater than 1, maybe 2 or 3? How to deal with that? That's what we are going to see here. So the theorem of least work says that dou u by dou r equal to 0. Okay, when there are more than one redundant, okay, for example RB and RD, we have two reactions and those two are redundants. How they will come, we'll see it in a few minutes. So when there are more than one redundant, as per theorem of least work, dou u by dou r1 is 0. Similarly, dou u by dou r2 is also 0. For any redundant, the partial differentiation of strain energy with respect to that redundant is 0. That's what theorem of least work is. Okay, so another difference what you are going to find is that when we have such conditions, the expression, we had reconstructed this equation in the form of m dot dx by ei equal to 0. So this m dot is basically dou u by dou r, dou m by dou r1 or dou m by dou r2. So how to handle that case is what we are going to consider in this particular video. So let's have a problem. So let the problem be something like this. Say I have a support here, another support here, and let there be a UDL in this span. Okay, that's all. So let this be the case. Let this be 2 kilonewton per meter and 2 meter, and let the EI value be constant. So now we are going to see how to solve this one. Let this be support A, support B, and support C. So when we get such a problem, you can say that if I am removing these two supports, it is a cantilever beam, which is a determinate structure. So I need to release two reactions, okay, two reactions, so as to make this a determinate beam. So let's try to calculate the ds value for this. So we used to do this. Once we get a problem, we used to convert it into a beam of forces. So let's try that one. So I'm going to have three reactions at the fixed end, one per roller, okay, and these are RA, HA, MA, RB, and RC, and there is a loading 2 kilonewton per meter. Now if I'm trying to calculate the ds value, degree of static indeterminacy, it is given by r minus e. What is the value of r? The value of r is the number of unknown reactions. So 1, 2, 3, 4, and 5. So 5 is the r value, and e is, this is a 2D beam, so I'm having three equations of equilibrium, sigma fx, sigma fy, and sigma m, which is going to give me the value as 2, which means that I need to have two redundants in this particular problem. Okay, so I'm considering RB and RC as the redundants, which means that if I'm removing RB and RC, what I'm having is a determinate beam. That's how we chose the redundants. So RB and RC are the redundants here. So now, earlier case we were having just one redundant, so we were having just one equation, an equation something like this. But here we have two equations. That is, one equation what we will be having is dou u by dou RB equal to 0. Similarly, dou u by dou RC equal to 0. We'll be having two equations in this problem. Okay, so we have two equations and basically two unknowns. So that's why we are having two equations. So now let's see how to solve it. Fine. So when I expand this equation in this form, what I'll be getting is integral m dou m by dou RB dx by EI equal to 0. That's what is given by this equation. What about this? This will give us the equation m dou m by dou rc dx by ei equal to 0. So what I'm doing is I'm going to call this parameter, that is dou m by dou rb, I'm calling it as m dot b. Similarly, this parameter I'm going to call it as m dot c. Okay, for convenience I'm doing that. Now what we need to do is we need to have that table where we want to have the different expression for bending moment for different segments and all those things that we used to do for earlier problems. We are going to try that now. So here, how many segments are required? So segments are decided based on the location of point loads. Here there are 1, 2 and 3 point loads. Okay, MA, RA acting at this point, RB acting here, RC acting here. So 3 point loads, which means I require 2 segments. Okay, segment 1 and segment 2. Now I am going to try to construct the table. And in the previous problem, we were doing some calculation before constructing the table because it was a simply supported beam. When we are looking for a simply supported beam, only if we have the reactions, we can start writing the expression for moment. But here it is not required because it is a cantilever. So we'll be always considering the origin as the one on the free end side. Hence, I won't be needing these equations to get the expressions. So that if I'm calculating, taking a section here, I'll be looking to the right. So these equations are not needed. These values are not needed. If I'm taking section segment 2, then also I'm going to look to the right. So these values are not needed. Hence, we can directly start writing the table. So segment, then E, L, O, M and m dot b, m dot c. Okay, m dot b and m dot c, these all are required. So depending upon the number of redundants, this table may go on increasing. If there are 2, we'll be having 2. If there is one more, then I'll be having m dot d, etc. If there is just one value, it will be simply m dot or m dot b itself. Okay, so now I'm going to try this. Okay, so I'm considering the segment 1. So the EI value of segment 1 is EI is constant, so I'm putting it as EI itself. Now I need to consider the origin. Where should I consider the origin? I am going to take a section in the segment 1. Okay, I'm going to take a section here. So which is the preferred origin? Should I look to the right or to the left? In the left there are a lot of forces, right there are just this UDL and this point load. So it's better to look to the right. So I'm considering point C as the origin. If C is the origin, what will be the limit? If this point is 0, this point is 2, so the limit is 0 to 2. Okay, then what about the expression for M? So I took the section. So we know that the distance x is always measured from the origin. C is the origin, so this is x. I'm calculating the moment. What I'm going to have is RC times x, right? RC is the force, x is the lever arm. So one value is RC times x. Is it plus or minus? Okay, is it plus or minus? We'll use the same convention. The point load is acting at the free end, it's sagging, hence it is positive. Then there is this UDL component. So the magnitude is 2 per meter. It is for x meter, so 2 times x, and the lever arm will be half of it, which is x by 2. So 2x times x by 2. And plus or minus, let's see. So the load is acting from top, it is hogging case, which is minus. So I have the expression for M. So this part I'm going to do later. So let's, so we are done with the segment 1. Now we are going to think about segment 2. Okay, segment 2. What about the EI value? EI is constant, so it is EI itself. What about the limit? So first I need to decide where the origin should be. Now I'm going to take a section here. So I can either look to the left or I can look to the right. If I'm looking to the left, I should have the values of RA, HA and MA, which I really don't have right now. Either you solve for it and then look to the left, or else you directly look to the right. Okay, if you are looking to the right, which should be considered as the origin? Okay, that's our choice. We can decide. So I can consider either B as origin or C as origin, whichever is okay. So let's consider C as the origin. Okay, just for a change. Even if you take B as the origin, no problem. If I'm taking C as the origin, this total distance will be the x. Okay, so this distance is going to be my x. Fine. If I'm considering B as origin, okay, just let's see. If I'm considering B as origin, this will be my x. Okay, so depending upon which I'm choosing, whether C or B, depending upon that, I will be having the x value. C is the origin, then this is x value. If B is the origin, this is the x value. So which one should be taken? Whichever is fine. So I'm going with say this one, C itself. If I'm taking C itself, what will be the limit? So which means C is the origin. So this is 0, this is 2, this is 4. So segment 2 is from 2 to 4. Okay, 2 to 4. And what about the expression for bending moment? Okay, let's try. I'm taking the section here. Okay, the section is taken here. So I'm looking to the right. So one force is RC, which is at a distance of x. Okay, I do not consider this or this, because now I'm dealing with the origin C for segment 2. So this is the x. So RC times x is the moment. RC times x is the moment. Okay, sagging or hogging? Load is acting like this, sagging, plus. Then what I have is this UDL. Okay, what about the moment caused by this UDL at this particular section? What will be the value? What is the force? 2 times 2 meter. That is 4 is the force of this UDL. Okay, 2 kilonewton per meter. Now it is for 2 meters. So 2 into 2, that is 4. The value is 4. What about the lever arm? Lever arm is the UDL, the CG of the UDL is at this particular point. And this point is at a distance of, how far it will be? This total is x. What will be this distance? This total is 2, so this will be 1. So x minus 1 is the lever arm for this UDL. You got this? So the lever arm for the UDL will be this distance, because the UDL is concentrated at this point. So the magnitude is 2 times 2 and the lever arm is this. So I'll be getting, the magnitude is 2 times 2 and the lever arm is x minus 1. Now I need to check whether it is positive or negative. So UDL is acting from the top, it is hogging, hence it is negative. Then I have another force. Okay, if I'm taking this section, there is another force RB. So what is the effect of RB? RB is the load. The lever arm is this distance. This distance is the lever arm. How much is that? X minus 2. Okay, so plus RB x minus 2. So that's the expression for bending moment for that particular section. Fine. Now we need to have these two. So before finding this, I want to reduce these two equations into some simpler format. This is a very long expression, so I'm just reducing it to simpler format. So this expression, say this expression, okay, I'm writing it here, that is, I'm calling it as MB, right? This is in segment 1, okay, segment 1, so it is M1, okay, segment 1, M1 is equal to 2 cancels out, so what is left is RCx minus x square. Okay, what about this? If I'm reducing it, what I'm going to get is M2 is equal to RCx 2 times 2, 4 into x, it is 4x, so minus 4x, then minus 4 minus 1, so plus 4, and here I'm going to get RBx minus 2RB plus RBx minus 2RB. So now what is the next step what we are going to do? The next step, we are going to integrate this in terms of x, okay, with dx. So I'm going to club the terms with the different powers of x. So here the maximum power is x raised to 1. So I'm clubbing all the terms with x raised to 1. So what all are having x raised to 1? RC, okay, minus 4 plus RB. Okay, those are the terms with x raised to 1. And what about x raised to 0? 4 and minus 2rb. So plus 4 minus 2rb. Okay, here it's already arranged in the terms of x power, so we can directly use that, and this is the expression for m2. And if you're wondering why I'm doing this, okay, this is required when we go for the integration, or else our integration statement will be so long that it's going to be very tedious to solve. So this is the easier approach. Now I'm going to calculate these two parameters. M dot b is basically dou u by dou rb. Okay, dou u by dou rb. Sorry, not dou u, dou m by dou rb. So I need to differentiate it with respect to rb. When I differentiate this with respect to rb, what I'm going to get? 0, because there is no rb here, no rb here. So when I do differentiation, these are constants, so I'm going to get 0. What about this term? This term becomes 0. This term again 0. What about this? This will give me the value x minus 2. Okay, when I differentiate it with respect to rb, I'm going to get x minus 2. Now I have this m dot c, that is dou m by dou rc. So when I differentiate this with rc, I'm going to get x. Okay, from here I will be getting the value x. This is 0. Here I'm going to get x, and this is 0. This is 0 because I'm differentiating with rc. So this is a constant. So this term also gives a 0. So this is the complete table. Okay, now we have the complete table with which we are going to do the rest of the calculation. Okay, so we have the expression for m1, m2, and we have the m dot b and m dot c values. Now let's try to calculate it. So we are continuing with the calculation. So I'm keeping the first page apart. So now we have two statements. Statement 1 is dou u by dou rb equal to 0, which implies integral m dot b dx by ei equal to 0. This is not the m dot b. Okay, so I'm going to try that. So I'm taking back this paper. So first we are going with m dot b. So we are going to consider these two and these two. So when we multiply m with m dot b for segment 1, m times m dot b is going to be 0. So I can directly substitute the first limit, that is 0 to 2, 0 dx by ei from the segment 1. Okay, what about segment 2? Segment 2, this is the expression for moment, and m dot b is x minus 2. So this equation we have reduced it into this format. So we'll work on this one. Okay, so what we have is plus integral, the limit is 2 to 4. 2 to 4 rc minus 4 plus rb times x plus 4 minus 2 rb, that is my m2, times m dot b, which is x minus 2 for segment 2. So multiplied by x minus 2 dx by ei equal to 0. Okay, so that's what the expression dou u by dou rb equal to 0 gives. Now I need to do this. So I'm going to try this. So I'm going to expand it. So I'm going to multiply it with x minus 2. This term I'm going to multiply with x minus 2. What I'm going to get is this become x square. So integral 2 to 4 rc minus 4 plus rb x square, x times x, x square, plus 4 minus 2 rb times x. Okay, so that is done. Now I need to multiply it with minus 2. So minus 2 rc minus 4 plus rb x, then multiply with this. So minus 2 times 4 minus 2 rb dx by ei equal to 0. Okay. Now ei is a constant. If I take this ei outside and if I transfer it to the right hand side, ei vanishes because right hand side is 0. So now I just need to think about this. So what happens when I integrate this expression with dx? Okay, so there is x square which will become x cubed by 3. This x, and there is these two terms are having the magnitude as x, so we can reduce this before substituting the limits. So I am writing it again. So integral rc minus 4 plus rb x square. Now I am going to expand these two and I am going to get the values. So what will this become? Plus, there is 4 here, minus 2 minus 4. When I multiply these two, I am going to get it as plus 8. So 4 plus 8, 12. Now minus 2rb, minus 2rb. So it becomes minus 4rb. Then what I left is minus 2rc. Minus 2rc of x minus, so I'm just taking this 4 inside. So what I'm going to get it, 8 minus 4rb dx equal to 0. This ei I took to the right hand side, so it becomes 0. Now this is something which is manageable. If we don't do this, this expression itself is going to consume this whole page. Okay, because this is a long expression. When I multiply it with x minus 2, I'm going to get an expression which is going to fill this page itself. So this is a better way of handling it. Now we can integrate and substitute the limits. So x square becomes x cubed by 3. So this is basically rc minus 4 plus rb x cubed by 3. The range is 2 to 4 plus 12 minus 4rb minus 2rc. X become x square by 2 in the limit 2 to 4 minus 8 minus 4rb. Okay. Integral dx is x in the range and the limit 2 to 4 equal to 0. Now this is an expression. Now I just need to substitute the value of 4 and 2 in here, and I'll be getting an expression which I need to solve. Okay, so this expression will be having two unknowns. One is rb, other one is rc. So I'll be getting an expression in terms of rb and rc from the first equation. Similarly, from the second equation, that is dou u by dou rc, I'm going to get another expression which will also be having rb and rc involved. So I'll be getting two equations, and in those two equations the unknowns will be rb and rc. On solving those two equations, we'll be getting the value of rb and rc. That's what this strain energy method of solution for this. Okay, so I'm going to give you the expression when I substitute the value of x in this equation, substituting the limit in this equation. We are going to get an expression which is going to look something like this. Okay, so I'm skipping one step. That step involves 4 cube minus 2 cube by 3. I'll be calculating this value. 4 square by 2 square by 2, this value. 4 minus 2, this value. And I will be clubbing all the rb, rc and constant terms together. And I'm going to get an expression which is going to look something like this. 2.67 rb plus 6.67 rc minus 18.68 equal to 0, which is my equation number 1. Okay, from dou u by dou rb I got my equation 1. Now I need to get the second equation. Second equation I will be getting from dou u by dou rc. So now let's see how to get that. Okay, so I'm taking a fresh page, and in this I'm going to consider the dou u by dou rc equal to 0. Okay, which is basically integral m dot c dx by ei equal to 0. So now we are going to go with the m dot c values. So m dot c values are available, m values are available. So here there is no term that is going to get 0. So we need to try both. Okay. So I'm going to go for the segment 1. The segment 1, m1 is rcx minus x square. So it's integral. The limit of segment 1 is 0 to 2. 0 to 2 rcx minus x square, that is my m. M dot c is x, so multiplied by x dx by ei, right? Plus the second segment, limit is 2 to 4. 2 to 4, expression for moment is this one. So I'm going to substitute that. X rc minus 4 plus rb plus 4 minus 2 rb, okay, that is my m, and m dot c is x dx by ei, okay, equal to 0. This ei constants, I'm taking it as a common term, taking to the right side, it is 0, so those trouble goes away. So what left? So when I do this integration, what I'm going to get is rc x square. Integrating, I'm going to get rc x cubed by 3 in the limit 0 to 2. What about this? Minus x cube. So it's going to be x raised to 4 by 4 in the limit 0 to 2. So that part is done. I'm going to the right hand side. So I need to multiply it with x. So this becomes x square. So integral x square dx is x cubed by 3. So it is going to be rc minus 4 plus rb x cube by 3 in the limit 2 to 4 plus this term. It is multiplied with x. So integral x dx is x square by 2. So 4 minus 2 rb x square by 2 in the limit 2 to 4 equal to 0. Okay, now we are going to expand this. So 2, so it is x cubed by 3, which is basically 8 by 3. What I'm going to get is 2.67 rc minus 2 raised to 4 divided by 4, which is basically 4, plus this term rc minus 4 plus rb times 4 cube minus 2 cube divided by 3. What I'm going to get is 18.67 plus 4 minus 2 rb times, this is 4 square minus 2 square divided by 2, which is 6 equal to 0. Okay. The rest of the calculation I'm doing it in a new sheet because that data will be required for the further calculation. So I'm going to I have this expression. Now I'm going to club the different terms together. So all the terms that is having RB is I'm going to put it together. So there is going to be 18.67 from here, and this is 6 times minus 2, that is minus 12, plus now the RC terms. So I'm going to get 2.67 from here, and here the value of RC is 18.67. So plus 18.67. There is no RC term here. Now I'm going to talk about the constants. So I'm going to get a minus 4 from here. Minus 4 times 18.67. Then I'm having 6 times 4, that is plus 24 equal to 0. So now I'm going to continue the calculation from here. So when I try this, so I'm just substituting the values in the calculator, and I'm going to check what I'm going to get. So 18.67 minus 12, what I'm going to get is 6.67 RB plus 2.67 plus 18.67 is going to fetch a value 21.34 RC plus, what about this value? So minus 4 times 18.67 plus 24 is going to give me a value minus 54.68, and that's my equation 2. So the equation 1 we have already constructed in the from the previous sheet. I'm taking it here. So it is 2.67 RB plus 6.67 RC minus 18.68 equal to 0, which is my equation number 1. Now I just need to solve these two simultaneous equations. So there are two unknowns and two equations. It can be solved using a calculator, and on solving it we are going to get the answers. So let's try solving it. And on solving it, I'm going to get the value of RB as 2.61 kilonewton and RC as 1.75 kilonewton. So I have the values of the two redundant reaction. Now the rest of the part is what we learned from engineering mechanics. So we have a beam in which there are few forces acting. So I'm reconstructing the beam here. So what we have here is a beam. There's a fixed support RA, HA, MA, and I have the value of RB, which is 2.61 kilonewton acting here, 1.75 kilonewton acting here, and there is a UDL of 2 kilonewton per meter. This is 2 meter, this is 2 meter. Now it's just a matter of application of the three equations of equilibrium, and we are going to get the solution. It's a very quick solution. I will do that. So first I will be trying sigma fx equal to 0, which will give me, I need to have a sign convention. I'm taking all the forces to the right as positive. HA, the only force in the horizontal direction is HA, so HA equal to 0. Then sigma MA equal to 0. If I attempt that, I'm taking moment with respect to this point. So the moments are, one is MA, okay, MA is clockwise. Then 2.61 times 2, it is anti-clockwise. So minus 2.61 times 2. Then minus 1.75 times 4, because the lever arm is 4 meter. Then this UDL effect, it is 2 times 2, and the lever arm will be this point, which means 2 plus 1, that is 3. Okay, are there any other forces? Nothing is there, equal to 0, which implies MA is equal to, you are going to get it as 2.61 times 2 plus 1.75 times 4 minus 2 times 2 times 3. We are going to get the value as 0.22 kilonewton meter. Now the only thing left is the RA value. To get that, I can use sigma Fi equal to 0. I'm considering everything upward as positive, so it is going to give me the relation as RA plus 2.61 plus 1.75, and this is acting downwards, minus 2 times 2 equal to 0, which implies RA is equal to 2 times 2 minus 1.75 minus 2.61. I'm going to get it as minus 0.36 kilonewton. So that's the end of the problem. I have the value of RA, I have the value of HA, I have the value of MA, RB and RC. So this is how we solve it using strain energy method. I know that you might have felt this as a very long problem, okay, because I was keeping explaining and doing it. That's why this much time has been taken. And you should know that whenever the number of redundant increases, the strain energy method is not the most efficient method. There are different methods for analyzing beams having higher degree of indeterminacy. So this is a basic method which is very practical and very easy when we are dealing with structures having single degree of indeterminacy or maximum 2. You have seen already when it is 2 how lengthy the calculations are going to be. Okay, so this is how we do the analysis for indeterminate beam having degrees of static indeterminacy equal to 2 using the strain energy method. Thank you.